So, what if I told you that two of the absolute biggest mysteries in all of cosmology, dark matter and dark energy, might not be real? At least, not in the way we think. We're about to dig into a new physics paper that proposes exactly that. And honestly, it could completely flip our understanding of the universe on its head.
And this is the central question, right? For decades, we've been on this massive hunt for some exotic, mysterious particle that explains dark matter. But what if we've been looking in the wrong place entirely? What if the answer isn't a what, but a where? What if the secret is woven into the very fabric of space-time itself?
To really get what this new idea is all about, we have to go back, way back, over 100 years actually, to a paradox that stumped even Albert Einstein, a real puzzle that sits right at the heart of his theory of general relativity. Okay, so let's break this down. Einstein knew that a gravitational field has to contain energy. I mean, it moves planets, right? And according to his most famous equation, E equals mc squared, energy and mass are basically interchangeable. So if gravity has energy, that energy should create more gravity. It's kind of like a snake eating its own tail. The problem was, every single time he tried to write down the math for this energy of gravity, the whole thing just fell apart. He came up with this thing called a pseudo-tensor, but it had this, well, fatal flaw. Imagine you have a ruler, but the inches and centimeters on it literally change depending on how you're holding it or where you're standing. That's kind of what this pseudo-tensor was like. It gave you different answers depending on your frame of reference, which in physics means it's pretty much useless. For over a century now, this problem of pinning down gravity's energy has been one of those huge unsolved mysteries. And you know, this whole thing really just points to the biggest clash in all of physics, the battle between general relativity and quantum mechanics. You've got relativity's smooth, flowing, continuous spacetime over here, and quantum mechanics' lumpy, choppy, quantized world over there. They just don't play nice together. And this is exactly the gap that this new paper is trying to bridge. So how in the world does this new theory try to solve a century-old problem? Well, it starts by doing something pretty audacious. It completely reimagines the fabric of reality itself, trying to finally connect that smooth world with the lumpy one. The paper basically says space-time isn't a smooth, continuous sheet. It's quantized. Seriously, think of a TV screen. From your couch, it looks like a perfectly smooth picture. But if you get right up close, you see it's made of millions of tiny individual pixels. This theory suggests space-time is just like that, made up of fundamental, indivisible little packets of energy. A pixelated universe. So, how many of these space-time pixels are we talking about? The paper actually calculates it, all the way from the smallest possible scale, the Planck length, up to the edge of the observable universe. And the number they get is 10 to the power of 60. That is a 1 followed by 60 zeros. I mean, that's an outrageously large number. We're talking more fundamental units of reality than there are atoms in our entire solar system. Okay, so the universe is made of pixels, but what's really fascinating is how the paper says these pixels behave. See, it's not just that they exist. They have a very specific shape and a dynamic to them, which is described by a really cool mathematical tool called Ricci flow. Ricci flow is basically a set of equations that describes how geometry or curvature evolves over time. The best way to picture it is to imagine a metal plate that has some really hot spots and some cold spots. What happens? Well, the heat naturally flows from the hot areas to the cold ones, evening everything out, right? Ricci flow does a very similar thing, but for the curvature of space-time itself. It smooths out the lumps. Now, inside this flow, you can get these special, incredibly stable structures called solitons. A soliton is a wave that just refuses to dissipate. It holds its shape perfectly as it moves. The classic example is a perfect smoke ring that just keeps on going. In this theory, a Ricci soliton is exactly that, a perfectly stable, self-contained, self-gravitating little packet of energy. It's a piece of geometry that holds itself together.
And here it is. This is the big connection. The paper's key insight is that those pixels of space-time we were talking about are these Ricci solitons. So it's not just that the universe is made of discrete chunks. Each one of those chunks is a stable, self-gravitating packet of energy. This is a massive change in how we think about the vacuum of space.
All right, so if space-time is really made of these little energy packets, what does that actually mean for the huge mysteries out there in the cosmos? This is where the theory goes from being interesting math to something potentially revolutionary. Let's start with dark matter. The theory says that dark matter isn't some new particle we have to go out and find. It's just a Ricci soliton, one of those pixels of spacetime, that's been excited into a higher quantum energy state. Think of it like a localized, stable lump of pure vacuum energy that's creating gravity, just like dark matter seems to do. So what about dark energy? The stuff that's making the universe expand faster and faster? Well, according to this paper, that's even simpler. It's just the ground state, the lowest possible energy level of all those space-time pixels. It's the baseline energy of the vacuum itself, and that energy is what's pushing everything apart.
And this is what makes the whole idea so compelling. When you look at the math, the properties of solitons just happen to perfectly mimic how we see dark matter behaving. Dark matter forms these localized clumps or halos around galaxies. It doesn't seem to interact with much. Well, guess what? Solitons are localized lumps of energy that hold their shape and stay stable even after they bump into each other. The math just fits. It's pretty amazing.
But the implications here, they don't stop with dark matter and dark energy. This new model builds to an entirely new definition of gravity itself. I mean, if this is right, it doesn't just solve a cosmic puzzle. It forces us to completely rethink what gravity fundamentally is. So the paper totally reframes gravity. It says, think of the vacuum of space, with its base-level energy, as a heat source, and normal matter, stars, planets, you and me, acts as a heat sink. Gravity, then, isn't a force pulling things together. It is the physical flow of space-time itself, moving from the high-energy vacuum toward the low-energy matter, and it just carries things along for the ride.
This quote from the paper really gets at how deep this idea goes. It's saying that as an object falls into a strong gravitational field, its actual location becomes more uncertain, more blurry because of these quantum vacuum effects. And the size of that blurriness is what actually defines the object's energy. It's a totally new way to think about what energy even is at the most fundamental level.
And that leaves us with this incredible, mind-bending question. What if gravity isn't a force that acts in spacetime, but is simply the behavior of spacetime itself? This whole theory paints this incredible picture of a pixelated, flowing universe that's carrying all of us along with it. It's a truly fascinating and, who knows, maybe even revolutionary new way of looking at our cosmos.